Let's look at one moment to the concept of conjugate acids and bases, an acid-base pairs, and what does that mean? When you have an equilibrium, what we call an acid-base equilibrium, you have, let's say, an acid. In this case, instead of using hydrochloric acid, HCl, I've used a generic acid called HX. This is our acid. It reacts with a molecule of water. So the HX, our acid, is going to donate one hydrogen ion, in this case to the molecule of water. So the compound HX is reacting as an acid, donating hydrogen ions. The molecule of water is accepting those hydrogen ions. If it's accepting hydrogen ions, then it is behaving as a base. And that's why we call it acid-base chemistry, because for a compound to donate a hydrogen ion, there must be another compound to accept it. If not, the reaction will not happen. For a compound to accept a hydrogen ion, behave like a base, you need another compound next to it that can donate that hydrogen ion. So the acid, that's what we call this acid-base chemistry, not only acid chemistry or basic chemistry, because you need an acid and a base, and they react with each other. One donates hydrogen ions, one accepts hydrogen ions. And even when you're talking about, oh, I only have hydrochloric acid, I only have phosphoric acid, I only have sodium hydroxide, you have another compound in the medium. Even if you don't mention it, you will have the water, which is the case. So, but let's now look at the reverse reaction. So the reaction going the other way. Let's look at this anion X minus, and let's go and what happens if you look at the reaction going from the products to the reagents. If I look at this X minus and I look at how it appears as a reagent, if the reaction was going that way from the products to the reagents, that X minus, that anion, would have accepted a hydrogen ion to form the compound HX. So actually it is behaving like a base because it's accepting hydrogen ions. So it is behaving like a base, and we call it conjugate base. So it didn't come from a box, it didn't come from a flask, it came from, I made an acid react with a base, I made my H plus react with water, and I generated this anion X minus. And if that anion reacts back, it will form the acid and it will behave like a base. If I look at the water, when the water reacted to accept the hydrogen ion, it formed the cation H3O plus. If I look at the reaction going this way, going from the products to the reagents, so I've got the H3O plus that goes to water. Look what's happened there. It has lost one hydrogen ion. It has donated a hydrogen ion. If you donate a hydrogen ion, then you are an acid. But to clarify that it's not just a random acid, it's an acid that came from a reaction from a compound that came before a base and that reacted to form that, we call it conjugate acid. So when an acid reacts, it liberates its conjugate base. When a base reacts, it liberates its conjugate acid. And sometimes you will read, like for example, you have this hydrochloric acid, it's an acid, and its conjugate base is the anion chloride. So that's what we call a conjugate acid-base pair. It means the acid and the base that will liberate if it reacted in water, or the base and the conjugate acid that would create if it reacted in water. I'm going to ask you to stop the video and have a go at this exercise. I've got 3 chemical reactions, they're acid-base reactions, and I'm going to ask you to identify on each reaction which compound is acting as an acid, which compound is acting as a base, and then in the products, which will be the conjugate acid and the conjugate base. So which compound is an acid, which compound is a base, and for the products, which is the conjugate acid, which is the conjugate base. Stop the video now. Okay, let's have a go. I hope you have a go at doing the exercise. How would I go about resolving this? Well, the first compound, HBr, I can tell you it's called bromidric acid, so it is an acid. But in case I didn't realize it was an acid, if I look at how bromidric acid is as a product, I see that it has lost the hydrogen. So it was able to donate a hydrogen ion. So if it donates a hydrogen ion, this is most definitely an acid. So even if I didn't know that it's called bromidric acid, I will know this is an acid because of the chemical behavior. It produces, it donates a hydrogen ion, in this case to the water, and it produces the anion bromide. And the bromide would be the conjugate base for bromidric acid. So if bromidric acid HBr is behaving as an acid, I look at the water. Well, if I look at the water, what's happened to the water is H2O on the left-hand side, on the reagent side, and H3O plus in the product side. So it has accepted a hydrogen ion. And that's the definition of a base. Bases accept hydrogen ions. So water here is behaving as a base and is generating the ion H3O plus, that is its conjugate acid. I'm going to leave reaction number 2 for a second. I'm going to go straight to reaction number 3, and I will go back to number 2 in a second. So the final reaction, nitrous acid, HNO2. Even if I didn't know it's called, that has the word acid in its name, if I look at how it behaves from the reagents to the products, I will immediately know it's an acid because it has lost the hydrogen ion. Because it has not only lost the hydrogen, it has left a negative charge here. I don't know if you can see, tiny here. That means it has lost a hydrogen ion, this H plus entity, and generated the NO minus, the nitrous anion. So this would be my acid, or the acid, and this would be the conjugate base for that acid. And if I look at the water, it's similar to the first reaction. It's behaving as a base, because if I look at the product side, I see that from the reagent H2O to the product side, H3O plus, it has gained an H plus, a hydrogen ion. So that means that it has accepted hydrogen ions, it's behaved as a base, and it has generated its conjugate acid. So this would be the conjugate pairs, HNO2 and NO minus, and this would be the other conjugate pair, the water hydronium anion. Those are the conjugate pairs. Let's look at the reaction in the middle. Let's see what happens with NH3. It's the compound ammonia. If I look at the reagent to the product side, NH3 has become NH4 plus. It seems quite clear that it has accepted an H plus. It has accepted a hydrogen ion. If you accept a hydrogen ion, then you are a base. So even if the compound NH3 looks like, oh, NH3, HBr, HNO2, they all have hydrogens, but the chemical behavior is not the one of an acid. The chemical behavior is accepting a hydrogen ion, so it's behaving like a base. And it generates the NH4 plus cation. It's called ammonium ion. And that is going to be the conjugate acid to our molecule of ammonia. So NH3, NH4 plus, and a conjugate base acid pair. So if the ammonia has behaved as an acid, if the ammonia has behaved as a base, then the water has behaved as an acid. And if I look at the molecule of water and how it looks from the reagent to the product side, it goes from H2O to OH minus. So it has lost an H plus, but it has gone to the base. So in this case, the molecule of water is our acid, and the OH minus, the hydroxyl anion or hydroxide anion, is the conjugate base. So as you can see, two very different behaviors for the water. It sometimes accepts hydrogen ions and sometimes donates hydrogen ions. A few examples of some common acids and bases that you can find in your kitchen or in people's kitchen. And as you can see, I don't know if you have noticed that some of the acids, acetic acid, citric acid, ascorbic acids, they have hydrogens that, yes, so they are Bromston-Lowry hydrogen acids. They donate hydrogen ions. But look at, for example, at the example of the aluminium salts. This is a sodium aluminium sulfate hydrated. It's the aluminium that behaves as an acid because it's aluminium 3 plus. That, not according to Bromston-Lowry, is not an acid, but according to Lewis, accepts electrons because it has positive charges. It can behave like an acid. And if we look at the bases, very common, well, in many cases very common as household cleaners, ammonia, sodium hydroxide. Look at others like, for example, sodium carbonate or sodium phosphate. They don't have hydrogen ions, they don't accept them or donate them, they are not there, but they can still be defined as a basis. From the Bromston-Lowry definition, the idea that if you have something with a negative charge, carbonate has 2 negative charges, it can accept hydrogen ions, so it would be a Bromston-Lowry definition of a base, but also according to Lewis. If you're a base, you have electrons you can donate. Well, the CO3 2- has electrons, the anion phosphate has electrons that can be donated. So in that case, you have a mixture of different types of bases, from typical Bromston-Lowry bases to Lewis bases to an Arrhenius base, for example, sodium hydroxide, NaOH, that will liberate OH-.